Our final segment on the forces unit will be that of tension. We talked a little bit about it before in our basic forces discussion, where we had strings going over the top of a table and the strength of pulling on a string and so forth, and what does that mean. Today we want to look at that in a bit more detail, and we'll look at one-dimensional and two-dimensional cases and give you a chance once again to use our ability to solve vector type problems. Thank you for watching. One of the questions that you will encounter are what we call two-dimensional tension questions. And this gets us back into our world of 2D vectors. Now there's a number of subtleties to this, and I'm going to do them in sequence. So let's just suppose we have a bar here. We have some kind of a mass being pulled downward. We'll have a ring here. So there's a tension here. There's a tension here and a tension here. Okay? And we'll have angle A and angle B. So what we're going to say here is that angle A is not equal to angle B. So you have to make sure you remember that. And often we ask, so this is TA, TB. They want to know what are TA, TB. This is very typical questions. And I'll put here not equal, because and the only way these are equal is if A and B are equal, and that will not be the case. You have to figure it out. Now, one of the most important problems here is choosing a fiducial. And the neat part about it is that it doesn't matter which one, but you have to be careful. So let's look at it. We have three logical positions upon which to choose. Let's use some Greek letters. We've got alpha, we have beta, and we have gamma. So we can choose our reference here from the bar. We could choose our reference from the ring, where the different strings connect. Or we can choose our reference from just above the mass. So let's see what happens here. We'll make a little table. Okay, so we're going to say our frame of reference here. And we're going to say we'll have TA, TB, we'll call this one TC, and we're going to use alpha, beta, and gamma. So let's look and see in the general point here, if we use the bar as our reference, are the strings pulling down from the bar, or are they pulling up? They're going to be, as you can imagine, being pulled down. So TA, TB, and TC point downward. If we choose the ring, TA and TB have to point upward, but TC will point down. If we choose gamma, they're all pointing up. Now this isn't all that difficult, but here's the point that all of you must remember, is that the angles, let's write that a little bit differently, because we have to get our theta A, theta B, and theta C angles must be consistent with the frame of reference of the fiducial point. Now I'm going to give you an example here, but let's just have a look at it. We'll just take this particular one here. If B, okay, if B equals we'll just say B is equal to 60 degrees. Okay? So then I'm going to put it over here. I don't know if it'll show in the video. We can try it. So B here. So for the alpha, they're pointing down. So this is 60 degrees. So then it would be 180 plus 60. So B, angle B would be 240. It's pulling down yet, no, it's pulling up in the second one. Now it's going this way. Okay? And the angle is only 60. So then we have 60 here, and it's pulling up in the final one, which is also 60. So what's really important, and this is just an example for angle B, you have to deal with angle A and C as well, is you have to remember, and it's none of this is all that difficult, but it is extremely important that, and it is critical to the question, that first you choose the fiducial. Sometimes it's chosen for you depending on the question. Sometimes you get to choose. You have to recognize the consequences of these vectors, which way they're going to be pointed based on your fiducial choice. And from that, you have to make sure that your theta A, B, and C all reflect that. Okay? So theta C, for example, just because we can infer it very easily, is pointing straight down. So what's that? That's an angle of 270 from the plus X all the way around to here. If it is going the other way, it's 90 degrees. So it's very important that you set up your frame of reference and understand what you're doing. The calculations themselves are not all that difficult. But if you don't set this type of question up, you're in big trouble. So please review this and make sure you understand it. And I'll do an example in the next panel. So you have, in this particular example, I have got an 80-degree angle here. Here's my bar. I have a 30-degree angle here. Remember that this does not have to be a right angle here. Okay, so let's get away from all of that. And so you don't have anything that can help you there. We're going to use our fiducial here at the bar. So we're going to base everything as if we're referencing it from here at the alpha. So because of that, we need to measure everything from the plus X counterclockwise, all our angles, just like I have been talking about before when it came to 2D kinematics, and we continually approach this exactly the same way. If you think this angle is 30 degrees, you do not understand what you're doing, and you need to go back and understand why that does not work. No more so than this one being 80. This force here is pulling in this direction here. The 30-degree direction is this one. And so right away you're in trouble. A lot of students, as I said before, somehow seem to have an allergy to angles greater than 90 degrees. We must get away from that and be okay with these large angles as appropriate that represent our circumstance. So once again, from the plus X all the way around to wherever it is, depending on the direction of the vector, in this case it's going to be 180 plus 80 gives us 260. And of course, this one's pulling straight down, so it's around and 90 degrees. So we have the three angles, and then we know the force. Remember, this is a magnitude now. We're not dealing with negatives because in this particular case, we already have our angle established. So this is simply a magnitude. So the next thing we're going to do is take components. So let's see what we have here now. Well, first off, our vector equation, before we go any further, is going to be T sub C is equal to TA plus TB. So if I pull on TC, the force that I'm pulling here will be the vector sum of these other two, which is exactly what's happening. And if it isn't, then we would have motion, acceleration, something would change. But this is static. Okay? So let's have a look and see what we know. TAX is equal to TA. We don't know the tension in the A direction, so we can't say anything. We can write cosine of 330, and we'll figure those out in a minute. TAY is yet again TA sine 330 degrees, and we'll figure that out. TB b x is equal to tb, also unknown, cosine 260 equals tby is equal to tb sine 260 equals, finally, tcx is equal to tc, or we can use 98, I guess, if we want to be specific here. 98 cos 270, which equals 0, and tcy, which is equal to 98 sine 270, which is negative, equals negative 98. Now let's do these calculations and we'll come back. So you can check to see that you've got the right values here. And this is why it is so important to get the right angles and to follow through with cosine every time, because then you will get the valid arithmetic signs for your vectors and making your mathematics very easy. Okay, I'm going to rub this out a little bit now, and we'll start to solve this problem, which isn't very difficult actually. So we'll, there we go. So in x, we have t sub c, which is 0, equals 0.867 Ta minus 0.17 Tb. And in the y, we have negative 98 is equal to negative 0.5 Ta minus 0.98 Tb. Notice that Ta and Tb are magnitudes. And so are greater than 0. So if you solve this problem and you get a negative value, then it's going to be incorrect. Alright, so let's do a little more erasing here, and let's see if we can come up with a solution here. So first thing what we're going to do is we'll determine one of them in terms of the other, do a substitution, and we should be fine. So let's do it that way. We'll move this one over here, and we end up with Tb is equal to 0.867 divided by 0.17 Ta. And that then, with the calculation, is just fairly straightforward. 5.1. Now this makes some sense, because this is more vertical, and as such is probably going to carry more of the weight of this mass than this side stay is going to. So that's a bit of a clue to what's going to be happening here. So then we have negative 98, and when you substitute, don't get fancy, because you can get into some trouble when you do that. Ta equals, or sorry, I misspoke, minus 0.98 times 5.1 Ta. Now 0.98 times 5.1 is not going to be very different. So 0.98 times 5.1 gives us 5. And we're going to subtract, this will be negative 5, and we're going to subtract a bit more. So this is going to be equal then to negative 5.5 Ta, which is equal to negative 98. So come out and around, and Ta then, which will be of course positive, is going to be negative 98 divided by negative 5.5, which gives us a value of 17.8 newtons. And then we saw earlier that T sub B is going to be 5.1 times TA. So we're simply going to say 5.1 times 17.8, and we get 90.8 newtons. Now let's have a look at, just when this is finished, what it's telling us. Because one of the things you have to remember is that these two will not add to give us this. Remember, they're at different directions. So you need to think about it a little bit. Okay? The tension in this wire is pointing this way. The tension in this wire is pointing this way. The weight is pulling this way. So just to simply add them would imply they're all pulling in the same direction. If you believe that, then you don't understand the question. So it's really important. This two-dimensional stuff keeps showing up over and over again as we work through this course. And so, once again, we just follow exactly the same procedure as we always have. If you decided to put your fiducial here, none of this would make any difference, because you'd have your directions going different ways, you'd have your components would have slightly different signs, but the values of TA and TB that you would get would be exactly the same. Because once again, these are simply magnitudes, and then depending on where you put your fiducial will be depending on whether they're pulling up or pulling down. So you need to go over this so that if there is an assessment someday, you don't just choose 80 degrees, you don't just choose 30 degrees. You have to follow the algorithm that I have been trying to instill upon you for quite a while now. So there you have the issue of tension and how it works in these problems. And of course, in the 2D question, you can begin to see how powerful and how important it is to have a properly chosen frame of reference. Well, actually, in this particular case, it doesn't really matter which one you choose, but how important it is to be consistent to the frame of reference and know that you are, and this is part of your skill set. So this is where it's useful to play with that. I hope this has been helpful to you, and this is the last video in the forces unit. The next unit will be that on energy, work, and power. Thank you very much for watching.